Permutations and combinations, lesson 3. Permutations with restrictions and permutations with repetition. So it's kind of continuing what we did last lesson, but there's some more restrictions and changes to it that we need to consider. So in many problems, restrictions are placed on the order in which objects are arranged. In this type of situation, deal with the restrictions first. Excuse me. Many of the problems in this lesson can be solved using the fundamental counting principle. In how many ways can all the letters of the word orange be arranged if there are no further restrictions? So if we think here we have 7 tiles in the word oranges, we need to rearrange them. We can think of that as going 7 times 6 times 5 times 4 times 3 times 2 times 1, which is the same as 7 factorial. So that gives us 5,040. If the first letter must be N, so sometimes simplest to think of this using the fundamental counting principle. So if the first letter must be N, that means we only have one choice for the first letter, and then we go times 6 times 5 times 4 times 3 times 2 times 1 for the rest. So this is really just the same as going 6 factorial, and that is 720. What if, though, the vowels must be together in the order O, A, and E? So now, instead of arranging 7 letters, we are arranging the 4 consonants and the group of O, A, E. So we can think of this O, A, E as one group that's now locked or glued together. So they travel as a unit of the 3 of them. So we have that plus, the 4 consonants that are left. So we have the letters R, N, G, and S. That's the 4 consonants plus the package of vowels which we can move around. So this is really 5 factorial, which is 120. But the questions get a little bit trickier. So in how many of the arrangements of the letters of the word brains are the vowels together? So now it's not telling me an order of the vowels being together. It's just telling me that the vowels need to be together. So that means I have one option where I have the A first, followed by the I, and then I have the 4 other letters. So this would be 5 factorial arrangements because I'm arranging 5 things, the 4 letters B, R, N, and S, and my group of vowels, A and I, together. Or I could have the arrangement I, A, and then the 4 consonants. So this is still 5 factorial. So that means I have 120 choices. The word or tells me I'm going to add them up. So together there is 240 ways. The other way you could calculate this, though, is saying I have 2 factorial options for arranging those vowels. I can have the A first and then the I, so I have 2 choices for the first one and 1 choice for the second one. So that's to arrange the vowels times 5 factorial, which means I'm now arranging my 5 pieces together, which of course gives me the same answer as 240. Find the number of permutations of the letter in the word kitchen if the letters K, C, and N must be together, but not necessarily in that order. So K, C, and N, I need to arrange as a group, but it's not telling me the order. So that means I have to arrange K, C, and N, I have 3 factorial ways. Now, to arrange K, C, and N, they're grouped together, along with the letters I, T, H, and E, I have 5 things in total to arrange. So that's with my group of K, C, and M plus the other letters gives me 5 things I'm putting in an arrangement, which equals 720. The trickier questions are ones like this, where the vowels must not be together. So in order to know when the vowels must not be together, I could take a whole bunch of different options and add them together. Or I could take the total number and subtract the number of ways the vowels are together. Well, the total ways, so I have 7 letters in the word kitchen, so that's 7 factorial. Subtract. Well, how many ways do I have of arranging these letters if the vowels are together? Well, I have 2 vowels, so I have 2 factorial ways of arranging the vowels themselves, times. So now I need to group the other 5 letters along with the vowels that are grouped together. So I'm really arranging 6 things. So I'm going to go 7 factorial minus 2 factorial times 6 factorial, which ends up giving me 3,600 in total. In how many ways can 3 girls and 4 boys be arranged in a row if no 2 people of the same gender can sit beside each other? So here I am grouping 7 people in total, but no 2 people of the same gender can sit next to each other. So I really have 7 people here. 4, 5, 6, 7. So I have 4 boys, so a boy needs to go first because I'm going to have boy, girl, boy 2, girl 2, boy 3, girl 3, and boy 4, right? I need that order, otherwise I can't fit 7 people in. So then really all I need to decide is which boy goes where and which girl goes where. Well, the number of different ways I can place the boys is 4 factorial. The number of different ways I can place the girls is 3 factorial. So that means there are 144 total arrangements here. 6 actors and 8 actresses are available for a play with 4 male roles and 3 female roles. How many different cast lists are possible? So you could do this using fundamental counting principle, but remember we also have our permutations, which are sometimes simpler to use. So I have 6 male actors to choose from, and I have 4 roles. The reason this is a permutation, so we say that with permutations, order matter. So if I give one actor the role of Peter Pan, and then I give another actor the role of Captain Hook, that's different than if they switched roles. So if Bob was Peter Pan and Jack was Captain Hook in one arrangement, if I gave them opposite roles, I would end up with a different play. So order does matter in this case. So I have 6 male actors, and I need to place 4 of them in roles. And, so that means times, I have 8 female actresses, and I need to place 3 of them in roles. So again, you could use the fundamental counting principle for this as well. So if I do this on my calculator, then I have 360 times 336, which equals 120,090 different cast lists. Sorry, 120,960 different cast lists. Okay, so you can stop here and do some practice questions, or you can keep going. So now we're going to look at permutations with repetitions. So in the previous section, the objects in each set were all different. So what happens when there are letters which repeat within the same word? To examine this scenario, consider the following 4-letter permutations of a word without repetitive letters. So the word rose means we have 4 letters. We're rearranging them. This is 4 place 4. We have 4 letters. We're placing all 4 of them, and they make 24 different arrangements. Now, if we change the E in rose to an S, we get Ross, a word with 2 letters which are repeating. If we change all the E's in the above list to S's, we will get all the arrangements for Ross as shown in the list below. However, notice that the 24 original arrangements now became 12 different arrangements. So now things start to repeat. Right here I have Ross and Ross. Well, those are the same. And there's more repetitions as you go around. So there's really 12 matching pairs of 2 4-letter arrangements. Arrangements like R-O-S-E and R-O-E-S from the first list both became Ross, or R-O-S-S, in the second list, and count as only 1. So there are half as many, or 1 over 2 factorial as many permutations of Ross as there are of Rose. Hence the number of permutations of Ross is 4 factorial over 2 factorial, or 12. Now, what if we also change the O to an S? So now we get the letters R, S, 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 a word with 3 repeating letters with the arrangement shown below. So let's see how many repetitions we now have. So we now have 4 matching sets of 6 4-letter arrangements. So there are 1/6 or 1 over 3 factorial as many permutations of R, S, S, S as there are of rows. Hence the number of permutations of R, S, S, S is 4 factorial over 3 factorial, or 4. There's a pattern in the above list. If the letter appears twice in a word, we divide the total number of arrangements by 2. If a letter appears 3 times in a word, we divide the total number of arrangements by 3 factorial. So the following formula gives the number of permutations when there are repetitions. Now this formula is not on your formula sheet, so you do need to remember what we need to do with these repetitions. Okay, so it's important. This is not on your formula sheet. So find the number of permutations of the letters of the words Vancouver. So we look for repetitions in Vancouver. We have 2 V's. So to do this then, we take our n factorial. How many letters do we have? Well, there's 9 letters in Vancouver. And we're going to divide out any repetition. So I'm going to divide by 2 factorial because I had 2 V's. This gives me the numbers 181,440. So what about the word mathematical? Well, mathematical has 2 M's, 3 A's, 2 T's. Well, to calculate this then, we take our 12 factorial, those 12 letters total. I need to divide out the repetition. So I'm going to divide by 2 factorial, 3 factorial, times 2 factorial. Make sure if you're punching this in one step, you put that bottom in brackets. And this is going to give me 19,958,400 different arrangements of the word mathematical. Brett bought a carton consisting of 10 mini boxes of cereal. There are 3 boxes of cornflakes, 2 boxes of Rice Krispies, 1 box of Cocoa Puff, 1 box of Shreddies, and the remainder are Raisin Bran. Over a 10-day period, Brett plans to eat the contents of 1 box of cereal each morning. How many different orders are possible if on the first morning he has Raisin Bran? So this is the case where it kind of makes sense about these repetitions. So we have 3 boxes of cornflakes. It doesn't make a difference in his life which of the boxes of cornflakes he eats. We just know that he's eating cornflakes one day. So it doesn't matter which one. That's why we need to divide out these repetitions. So they do tell us that on the first morning he has Raisin Bran. So that means after the first morning, he has still 3 boxes of cornflakes. So 3 cornflakes. He has 2 Rice Krispies. He has 1 Cocoa Pops. He has 1 Shreddies. And the rest are Raisin Bran. Well, it says he started with 10. So this is 6, 7. So there were originally 3 Raisin Brans. But it's telling us on the first morning he's having 1 of those. So really we have 2 Raisin Brans left. So we know the first morning he has Raisin Bran. So we're really just looking at the 9 boxes of cereal he has left. So there's 9 total. And we need to divide out our repeats. So I have 3 cornflakes, so I'm going to divide by 3 factorial. 2 Rice Krispies squares, so I'm going to divide by 2 factorial. 1 of Cocoa Puffs, 1 of Shreddies, so I don't need to do anything. If you divided by 1 factorial, though, it wouldn't make a difference. So you could put that in. And then I still have 2 boxes of Raisin Bran. So this gives me 15,120 choices. One thing this unit always makes me realize is that it's seemingly impossible how we ever make any decisions in life. So all we had was a container of 10 boxes of cereal, and somehow we need to choose between 15,120 different combinations of that. That's crazy. Okay, example 8. Paul and Catherine are considering the following problem. Find the number of routes from A to B if routes must always move closer to B. Paul arrived at the correct answer by tracing 10 routes on the grid. Catherine developed a quicker method. She realized that travel from A to B involves moving 3 units east, so that's 1, 2, 3 units east, and 2 units south, so that's 2 units south. And that the answer to the problem is the number of ways in which this can be done. So we need to take, let's say each one is a step. We need to take 3 steps to the east and 2 steps to the south. We can do that in any order. So to see that, how could we solve this using permutations? Well, in total, we essentially need to make 5 steps, or rearrange these 5 letters. We have 3 steps to the east, 2 steps to the south, so those are our repeats, which gives us 10 routes.